Hey there, can somebody give me a thumbs up on the audio and that you can see the slides? We good out there? I haven't heard anything yet. Okay, perfect. Thank you. Okay. Okay. Where we started, or we're going to start today where we ended on Wednesday. And we had this whole list of relationships between the Fourier transform and the function. And we got to this one where we looked at the convolution theorem, where if I have two functions in space and I convolve one function with the other, if I look at the operation in the Fourier space, that is equivalent to multiplying the Fourier transform of one function with the other. And this becomes very useful when we're designing filters and things like that. So you should know these properties. Some are going to be more useful than others, but it's a good idea just to, as an operational thing, to know these, but obviously you can look them up at any time. The convolution theorem, you can prove it to yourself that it's true, such that if I have, let's just do it in one dimension. If I have one continuous function g, another continuous function h, convolve them, take the Fourier transform of that resultant function. When I write that out when I write the Fourier transform out, and the convolution itself is here, and this is the Fourier transform, then because kx essentially here is just a fixed number and our integrals are all over dx and du, you can move certain functions inside and outside the integral because they just become numbers, and such that we have what's left here is the Fourier transform here of h, little h of x, and that shows up here. So now it's just a number dependent on kx, which is the parameter for this integral. And you can shift that outside, and then you get the Fourier transform of gu as the resultant. And so it's the product. Again, very important practical relationship. And when we go all the way back now to the modulation transfer function, where we look at the ability of a system to transmit higher frequencies. So the modulation transfer function drops as our spatial frequencies get higher. This means things that are at 1 cycle per millimeter are being transmitted through our system with higher amplitude than those signals that are at 2 cycles per millimeter. And this shows the continuous function. We can use the convolution theorem to understand how blurring is occurring in the Fourier domain. So this is the Fourier domain. We're in spatial frequency. And if we look at it at our image in the Fourier domain and spatial domain, so here is a picture, a sagittal image of somebody's brain in the spatial domain, right? So we have brightness as a function of position. And when we look at the Fourier coefficients of this function, right, it looks something like this. Oftentimes when you take the Fourier transform and display the coefficients or the magnitude of the coefficients, you'll display the logarithm of the magnitude, because the coefficients are so much higher in the center than the outside. You would just see a bright spike if you just showed it in a linear display. So this is the logarithm of the Fourier transform. So here, this represents basically a block of spatial frequencies that are found inside this image. If we modulate the Fourier coefficients with a modulation transfer function, that is, we multiply the center by 1, but as we go out to higher frequencies, we multiply numbers that are less than 1. So we're pushing down the relative amplitude of Fourier coefficients out here, right? So I've modified this Fourier transform, the Fourier coefficient such that it now looks like this, right? And when you take the inverse Fourier transform of these coefficients, you get this picture. And that means there just aren't as many high frequencies in that picture. It looks blurrier. And if we have a modulation transfer function that falls off even more quickly than this one, by the time we get out to these spatial frequencies, we're down at 0. And this is what the image looks like. So it's very blurry at that point. Recall that the center value of the Fourier transform, or the DC value of the Fourier coefficients, are the result of an integral, which is our function multiplied by the e to the negative j 2 pi blah blah blah, with kx and ky set to 0. So that function is just 1 e to the j that. And so that's just the integral under the entire function, right? And so that's what that point represents. It's called the DC value. So it's how much, stuff is there. Okay, so we're going to move to our next presentation, which is about sampling. And we're going to look at how we sample continuous functions and what is the sampling rate that we must achieve in order to accurately sample a continuous function. That's called the Nyquist criterion. So we all live in a digital age now where virtually every signal that you guys see or have ever seen in your life is digital. So it was transmitted over some, wire or Wi-Fi or something like that as a sequence of numbers, right? And whereas when I was growing up and I put a record on my record player, right, I had a little pickup that, it was a needle, and you put that thing down and it got dragged through a groove and it vibrated. And that those little magnets vibrating in that pickup caused a continuous voltage, right, which was the music, right? And it was encoded as oscillations in the vinyl, right? And so that is essentially a continuous, or a function, or an analog function. Along comes digital recording, and if I have my analog wave here, I can essentially sample discrete values of that analog wave and just remember those numbers, right? So I don't need the entire continuous signal. I just need to remember a finite set of numbers, and I can transmit that signal, right? And it's much more efficient, right, than carrying around analog signals, unless you can write down an equation for the analog signal. If you can write down an equation, then that's really efficient, right? If it's like sine x, sine kx or something, then you only need a few symbols. But that's not the case for recording. If you're recording somebody's voice, you very rarely write down an analytical function for the voltage of their voice, right? So it turns out digital is just much more efficient. You can compute with it much more easily. So that's the way it's done. And in medical imaging and any other imaging, that's the way it's done nowadays. So here is, finally, we get to a CT of somebody's chest. And we're going to look at the pixels that comprise this image. Okay, so it looks like a continuous function. We have up here, this is the chest wall of the patient. We're looking from the patient's feet towards their head. And this is an axial cut, it's called. So if you took a saw blade and cut them in half perpendicular to their spine, this is the view you would see. It's called an axial cut. The lungs are out here. This is the upper, or the superior portion of the heart, where you have the ascending aorta, the descending aorta that runs behind the heart. This is the left atrium, a pulmonary vein coming into the left atrium. This is the pulmonary artery going out to the lungs. And so radiologists, cardiologists learn to recognize everything in this picture, over with practice. If we zoom in and take a look at the central portion of the picture, so let's if we look at this part right here, this little square and that little dot will tell us we're in the right place. We zoom in, you can see we see high resolution features, but there's an interesting high resolution feature that probably is not real, right? If you look at this bright signal there, it looks like it's a stack of boxes, right? So that's not what's in there, right? It's not a stack of boxes. It's a continuous function until you get to the quantum domain, and we're never going to get down there, right? So these little boxes tell you the rate at which you are displaying values for this image. So a dimension of one of those boxes, let's say it's a 0.5 millimeter, is one way of saying, okay, what is the resolution of my picture? Well, the pixels are a 0.5 millimeter apart, right? However, your point spread function of your imaging system isn't necessarily, sampling rate of a 0.5 millimeter, right? This is just what's displayed here. Right? You should always display your pictures with pixels that have a few pixels at least inside the point spread function, right? You shouldn't have an image that is one box. It's a square that's lit up because your point spread function is inside that box. That's a bad idea. Use more pixels so that you see a blob, which is your point spread function, right? So if we go right in, you can see these boxes, and even on the edges here, you can see these boxes. So to display the image, we should really take these values and interpolate them. If these are truly the highest frequency we can, measure, we should take those values, interpolate them, and display them so it looks like that, right? So this just uses more pixels. And so now I get rid of that artifact, which are these boxes, okay? Again, it's a very quick and dirty way of telling someone what the resolution of your picture is. It's just the space between the voxels. If you go back to before we did that interpolation and you look at the curve through an object like this thing here, you can see these very discrete steps. So we have a very discrete looking image. When we do the interpolation, that's probably a more realistic version of what's in there. This is what's in there convolved with the point spread function of the system, right? So it's going to be blurred by the system, can't get around that. But at least we see the underlying truth just blurred with the point spread function of the system. That's a very interesting, this is the left main coronary artery, and it comes into the plane here and then goes out of the plane there. So it's just in the imaging plane for a brief section. So you can measure the dimension of it. And this is a little chip of calcium that's inside the vessel wall, the left main wall, right? That indicates that there was some kind of injury and then repair, right, to that vessel. And if you get a lot of these pieces of calcium, it's not a great thing, but Joe, you get them. Everybody gets them. By the time you're my age, you're going to have them in there. Probably about 15% of you would have coronary calcium or aortic calcium, something like that. But by the time you're my age, it's like 60% of people have it. So if you have a lot, it's bad. You should take statins. So let's look at sampling frequency just for the mathematics of this whole thing. If those of you who watched Dr. Liu's primer, he's talked about some of this, so it's a good combination with this lecture. So we have a delta X, or a distance between sample points here, and this grid of these samples, we can call basically a two-dimensional comb function or a two-dimensional sampling grid. Okay? Obviously, the samples are far too far apart here to be of any use to us at this point, other than there's an object there or not. If you increase the sampling rate by a factor of 2, so delta X between the sampling points goes down by a factor of 2, then we see these samples. Okay, so this is just setting up how we're going to do the math. If we have a continuous signal, and we assume this is sort of like a continuous signal, or it's continuous as far as we're going to sample down, right? So we have a continuous signal, fxy. We can generate a discrete signal, right? That is simply, all you have to give me is the point M and N. So I'm just going to enumerate what point I'm seeing in the XY plane. So X and Y is substituted by a single counter, right? We basically separate our samples by delta X and delta Y. And these are called the sampling periods. And then the sampling rate is 1 over the sampling period. So if you're sampling like 5 times a millimeter, you know, if it's 1/5 of a millimeter is delta X, then it's 5 samples per millimeter is your sampling rate. Okay. The sampling rate is usually in CT, it's fixed in the sense that we have a detector that's in place, and that's what we're going to use. We're going to shine a light and we're going to detect the image of the shadow. In the early days of CT, there was a source, there was one single detector, and both the source and the detector slid along the patient and produced views of what was coming through the patient. And then the whole thing would rotate, and then that would happen again, right? And so that's more like a continuous sampling. It's sort of integrated sampling. But it's very, very slow, right? So it's never done at this point. They quickly went to a set of fixed detectors that were close enough that you thought that was high enough resolution. So I have enough detectors along here per unit or distance that I'm at a high enough spatial frequency. And now most of the geometry is like this, where you have a single source, you have a fan beam coming from that source, you put a little hole and then a fan beam comes out from that source, and then you have a fixed set of detectors sitting there catching the shadow cast from something in this position. And in 3D, exactly the same. You stack these on top of each other. And then your object is in here in 3D, casts this 2D shadow on your detector array, right? So basically our fundamental frequency of sampling the shadow is set by the distance between these detector elements, right? There is some nuances here in that if I have an object very close to the detector, it makes a small shadow on the detector, so I won't get as many samples. If I pull the object up towards the source, right, the shadow gets bigger, right? And so I broadcast that shadow over more detector elements. And so that has to go into your thinking about what is the sampling resolution of this, right? Okay. So here's a modern CT scanner, X-ray sources here. We get a fan beam coming out, and again, it has fan beams in 2 directions, both in theta and in Z, right? There's a sweet spot inside the scanner. Anything in here can get imaged. And then there's about 1,000, I think it's like 892 detectors in this direction, right? And then that whole thing's going to rotate around. So we'll get projections with that type of sampling. If you look at what the detector array looks like hardware-wise, this is Z in this direction, right? And we'll call this direction theta. So I have about 892 detectors in this direction, 256 in this direction. And the way we make so many detectors is you break it up into little chips or chiclets. They're not silicon chips, they're like little chiclets. And they're inside here. I think I have a picture of it. Yeah, here they are. So this is Z now. So let's go back to this one. If I look along this way, along my detector, I get along this way. This is Z. And each one of these chips basically has an array, like a 32 by 16 array of individual detector elements on it. Pat them all in there together, right? And here's, it chunks in here like this. Again, this is Z. So I have 32 here. So I'd have 8 of those, right, in this direction to get 256. And up here, this is the material that creates the flash, and then you detect with a photodiode the signal down here. But it's broken up into this 32 by 16 array. And then you put them all together to make this huge array. Okay. All right. Oh, I guess it's 832 in this direction. I've been saying the wrong number. 256 in that direction. So let's look at sampling, how the mathematics basically of how sampling occurs. So here's a continuous function, is this pink thing, right? And now I'm going to decide on a sampling frequency or a sampling period, delta x, and we'll sample our function as we step along at that frequency, right? To create now a set of non-zero values at a finite set of points. I can still create a continuous function that is zero everywhere except at these finite values, right? So we can do calculus and all of that stuff. So big question is, like, if I want to take a picture of something and I want it to be an accurate picture, what is the sampling rate that I am going to choose, right? If you don't get there, right, if your sampling is too low, what are the artifacts that occur? Okay. And something to keep in mind is a criteria for determining that your sampling rate is high enough would be you can reconstruct the original continuous image from the sample points, right? So if I have an original continuous image and then I sample it, I have a discrete set of points over here. If just through interpolation and magic, I can reconstruct the exact continuous image, then I'm sampled high enough. So in MR, the way the signal is sampled is in the time domain. So we excite a radio frequency signal from the patient. So the patient is producing radio frequency energy from all parts of their body that have protons. And then you put a RF coil up to it that's tuned to, say, 64 megahertz if it's 1.5 T, right, or 128 megahertz if it's 3 T. You put that coil up and you listen, right? You look at the voltage per unit time from that signal. And you're going to make a super high resolution picture from that signal, which when I first saw it, I was like, what the heck? How do you do that, right? It's a radio frequency signal. These are the wavelength of that energy coming out of that patient is like measured in meters, right? So how are we going to make a picture that's on millimeter scale from that signal, right? So here's a time domain signal, say a voltage versus time in a coil. This is 150 milliseconds across here, and we're going to discretely or digitally sample that time domain voltage at a certain rate, and we're going to call it fs, right? So one way of looking and asking, well, what frequencies exist in this signal inside here, right? So I can take the Fourier transform of that signal and it will tell me, right? And if this is time domain, this is hertz, right? So it's basically, or kilohertz, what the frequencies are. And then we have these relative powers of frequencies in this signal, okay? So I've got a peak somewhere here around a kilohertz, between 500 hertz and 2 kilohertz. There's some kind of peak up here, but there's also some substructure to it, right? And then it fades out as we go to higher frequencies. What does it look like when I take this signal and I throw out all the points except every 8th point? So I keep a point, throw out 7, keep a point, throw out the next 7, keep a point. So I'm sampling at 1/8 of the sampling rate. So fs divided by 8. The signal looks like this when you plot it in MATLAB. Take the Fourier, transform of this signal, and you get this on the right here. That looks totally different than this, right? So, and it has some interesting features, right? In that it looks like it's the same function replicated over and over again, right? Looks like this thing gets replicated here, which gets replicated here, which gets replicated here. So now we've turned our continuous signal, by undersampling it, we've turned it into a periodic function, right? Which is kind of an interesting artifact, right? And so this is what you would call, if you needed frequencies up here, you're out of luck, right? So this is called aliasing, and it comes from undersampling, by not sampling high enough to basically detect frequencies that are up here independently. So a visceral pictorial view of what aliasing is if I have a high frequency sine wave and my sampling rate are these points along here, right? So this is what my signal looks like after I've sampled it. It's pretty obvious we've sampled this well enough, right, to detect this frequency, right? Because we have a very nice sine wave mapped out here. And so both frequency and phase, i.e. where the sine wave is on the time axis, are well sampled here. If I drop my sampling rate by a factor of like 10 or 20 or something like that, such that I only get a point here, I get a point here, I get a point here, and here, right? Same function underneath there, but when I ask what frequency do these points represent, it's this one, which is a lot lower than the high frequency or the highest frequency in that sine wave, right? So looking at this, I think we're oversampled, right? Just viscerally, just like gut feeling here. To sample this sine wave, I think we're oversampled, right? We got so many samples here. Who can tell me, just take a guess, how many samples do we need to sample this sine wave adequately? Just looking at the picture. What's the characteristic that we got to pull out of this picture? So if I took this sample, where should my next sample be in an adequately sampled sine wave? Probably, yeah. I heard somebody say about halfway, about to there, right? That makes sense, because then I would have a sample up, a sample down, up, down, up, down, up, down, right? And so that basically that's, the Nyquist theorem is I need 2 samples per period in order to sample a sine wave adequately, right? So it's twice the frequency of the sine wave itself, right? That's my sampling rate. We're going to keep going because we're behind here. These are all just examples of aliasing, but okay. So we're going to now talk about sampling mathematically, and Dr. Liu did this in his extra session, which you can watch the video. So a lot of this should be review. So we're going to define a comb function as this thing. It's the sum of delta functions that are displaced from the origin, by some unit, okay? So here I've got integer displacements from the origin, and this is called a sampling comb, okay? And each one of these is an equivalent delta function. It's just the sum of them all, right? And this is what we're going to call comb X. And important that comb X, it's not a finite set of numbers, right, that are non-zero, that are ones. It's a continuous function. It's defined everywhere on this domain. It's 0 everywhere except here, 0 everywhere except here, okay? So it's a continuous function. We can do it in 2 dimensions very easily just by adding y and a different integer, right? And so now we have a 2-dimensional comb. What else do we want to say about this? Oh, and then the sampling comb itself, we can describe as a continuous function in xy that have sampling periods of delta x and delta y. And when we look at the comb function, we also put out a normalization factor in the front of it, so that it's like how many samples per unit area kind of thing. So if these numbers get really small, this normalization factor will change to compensate. Okay. So that's all from the book. So the scaled, if we don't want to just be at integers, obviously, we want to be at our like delta x or sampling rate value for our comb function. And this is just the algebra for if I have a comb function that has delta x between each sampling spike, right? This is how I'm going to write it. Okay, well, we just kind of did that on the previous page. And this is what it looks like as a sum of delta functions. Okay. So here's our sampling comb where we have a delta x spacing, right? And it's going to generate a sampled version of our continuous function. And that sampled version will be 0 everywhere except for finite points at which it takes on the value of the function at that point. That's it. Okay. Okay. This function is a continuous function in X. And so when you're doing all of your proofs and everything mathematically, you can think of this as a continuous function. It is not the sequence of values, right? Which is kind of when we started talking about digital images, we said, well, all we're going to store is the sequence of values, right? This is the sequence of values right here, right? So that when you sum all of this up with the delta functions here, these coefficients are the finite sequence of values that you can stick on your disk and take with you, right? And that describes the function. Okay. Okay, we'll just set that. I think this is just an extension into 2D. Otherwise, I'm not sure why I'm looking at this. Okay, you can do it in 2D. Okay, back to our example. And if we want to look at the frequency components, right, we need to look at the Fourier transform of the comb function itself, right? And it turns out the Fourier transform of a comb function, kind of surprisingly, is a comb function. And the gestalt, I don't know how to describe the gestalt of that, but you can imagine that if you need to create a function, so in space, I have this function that is 0 everywhere except these little tiny spikes that I need very, very high spatial frequencies, an infinite number of them actually, to make a spike that is infinitely narrow, right? And so that's why when you get over to the Fourier side, you see a discrete set of sine waves that go in to making these spikes, right? So the Fourier transform of this function of a set of combs is this thing. And then when you plug in the delta x into this side, you find that the delta functions are separated by 1 over delta x, okay, as opposed to delta x. Okay, so if I have, do I have a diagram of this? Yes, I do. So if I have a comb function here of delta x, when I take the Fourier transform of that, I get a comb function. However, the spacing between the delta functions in the Fourier space is 1 over delta x. Okay, so as these get closer together, what does that mean? Like when I push these samples closer together by making delta x smaller, so I take my CT detector and it had delta x is 1 millimeter between each detector element. I now build a new detector that has a 0.5 millimeter, so I squish everything in by a factor of 2. Then the Fourier transform of that comb function, these will spread out farther, right? The replicants of these delta functions in Fourier space. Okay. So now, what is it to take the Fourier transform of our sampled function? right? So we now have a continuous function, gx, it's just a continuous function in space. We multiply it by our comb function, right, to get a sampled version of gx, which has this s as a subscript. And so what does that mean in terms of what it looks like in the Fourier domain, right? When you have, I've got a continuous function, it has a continuous Fourier transform. I now have that continuous function represented by these single points along it. Take the Fourier transform of that thing, right? It's still a continuous function. It's zero everywhere except these finite points. And so here we take the Fourier transform of this thing, and by the convolution theorem, remember, this is a product. Gx times the comb function is a product. And we just looked at this. So when we take the Fourier transform, it's the convolution of the Fourier transform of Gx with the Fourier transform of the comb function is the resultant Fourier transform of the two together, right? So that's kind of cool. So that means I've got this is my continuous function. This is its continuous Fourier transform, right? I convolve that with this, the Fourier transform of a comb function, which is a comb function, right? So I convolve it with a comb function, right? To get the continuous Fourier transform. And so that it looks like this, and then you can simplify the algebra down to this, okay? So what does this actually mean? I have a continuous function g, it's continuous in kx, right? But at each point kx, it turns out it's the sum of, g of kx minus n over delta x, where n goes from minus infinity to infinity, right? So at any point in this continuous function g of kx, the value at that point is composed of an infinite sum of values of this continuous function over its whole domain, sampled at certain places, right? So, which is kind of bizarre, but it, this is, if we look at it graphically, it kind of makes sense. So if I have this continuous function, g of x, and its continuous Fourier transform looks something like this, right? So at DC, it has a value, and then it rolls off to very low values, even 0 at some place. So this is my continuous Fourier transform of g of x. When I look at the Fourier transform of g sampled of x, so now it's just these finite points. When I do that from the math in the previous page, I get the original function here plus these replicants spaced at 1 over delta x. And so at this value, I have to say, well, it's whatever the continuous Fourier transform is here with n of 0 over delta x. So plus, and then you look at the value of this function here, right? And I add that in, and then I add in the value of this one here, and then the value of the next one. Right? So at any point here, it's actually the sum of all of these functions, right? Ideally, obviously, you want each one of these functions, these replicants in Fourier space, to just go down to 0 at a certain point. And that way, when you add them in here, there's nothing to add, right? And that's called a band-limited function. After a certain set of frequencies, it falls down to 0. And you don't have to worry about these replicants folding back into your original Fourier transform and causing aliasing, right? So that's the math of aliasing. And so what it tells you is if you want to avoid having a value here be the original continuous value plus these replicants, then you have to have the 1 over delta x, this separation between these two replicants. You have to have that separation greater than twice the bandwidth of the function, okay? So U is, if the frequencies that are in your original, the spatial frequency in your original functions are between u and minus u, and outside that, they all fall to 0, then you're okay. Because this spacing here, if it's greater than 2u, this will be 0 by the time it comes into this domain. Okay. If that isn't the case, then the replicants start getting closer and closer together, and you start seeing some very interesting phenomena in your Fourier transform where those overlaps are significant, right? It doesn't look like the right Fourier transform. You haven't sampled high enough. So if this is the case and you're seeing the Fourier transform and it looks really terrible, right, of your function, the Fourier transform looks terrible, what's your first thing? What should you do? If you have the option, you should go back and sample it again, right? Just try twice as many samples. And then maybe these will spread apart and you won't have this corruption. And if that doesn't work, try 4 times as many samples. So that, you know, so nowadays, because digital stuff's cheap, you just keep sampling at higher frequencies. The other thing you can do is, if your original function, if you're stuck with your sampling grid, right, before it hits your sampling grid, maybe you should filter it, right, so that when it hits your sampling grid, it's inside the Nyquist criterion, right? Exactly the same thing happens in 2 dimensions as we just did in 1 dimension. If my original function has, you know, Fourier coefficients that are inside this boundary, then I can pick a sampling rate such that the replicants of those boundaries aren't really crossing over. If I drop my sampling rate, I can start seeing this happening in 2D, right? So I'll start getting fold over artifact or aliasing. And this is, as we saw, when we undersampled this thing, right, we started seeing these low frequencies showing up, right, as power, right? So here's a visual example, or real, I like this example of you know, demonstrating aliasing. And so here we have in the plane, we have a sine wave that's going in, or it's a cosine actually going in the x direction, we'll say. And let's call this 5 millimeters. So, you know, I have 1 cycle per millimeter here is what it looks like. And let me take this off. And my sampling rate to generate this picture was 1 sample every 1/10 of a millimeter. So I got 10 samples between here and here, right? Or 50 samples between here and here, right? So they're pretty close together. I get 10 samples per sine wave. That should be high enough, like, to sample that sine wave adequately, right? Let's cut that in half such that our sampling rate now is 5 samples per millimeter, or 0.2 millimeters between. So delta x equals 0.2, and the function, when you just plot it, you know, on your computer, it looks like this. So it's starting to look a little weird, right? It doesn't look like a sine wave anymore. It looks sort of like a discrete function. If you do 0.3 spacing, you start getting something that has periodicity, but at a much wider period than the, you know, 1 cycle per millimeter. But it's still, you know, looks like a reasonable function. Here, 0.4, we get something that looks quite interesting. And then at 0.5, so we have 1 sample here and 1 sample here. So we have a sample up and a sample down, and a sample up and a sample down. And so that is what it looks like when you plot it over the same space. And that is the Nyquist frequency, right? Because now you have the frequency. You can still see, oh, I've got, you know, 1 cycle per millimeter in this function, right, from that plot. However, as we get higher, we start seeing some pretty bizarre patterns, okay? When we go past the Nyquist and start plotting these things, until finally, when we get to something that's 0.9 between sample points, we see this very low frequency function it's interfering, right? So the sampling grid and the function have this kind of interference pattern causing this low frequency modulation. You can see this a lot when you have a screen door or a pool screen or something like that, and then behind it, there's something that has another screen or another high frequency, and you take those two screens, and they're both sampling rates, right? And you just move one screen to, like, angle the screen to the other, then you're changing the sampling rate, and you'll see these very low frequency patterns emerge, right, between those two objects, right? Everybody's seen that, right? You're not crazy. It's just sampling theory. So if we assume highest frequency in object is 1 cycle per millimeter, then the Nyquist theorem tells you you got to sample at 0.5 millimeter separation, or twice that. Okay. So in CT, just saying, oh, we'll sample twice as fast, that's not an option, right? We've got a sampling grid, it's there, we're using it. And so we need some other way, right, to limit frequencies that are way beyond our Nyquist, such that it doesn't cause artifacts in the image. And so one way of doing that is to try and filter the signal from the object itself. It gets some filtering actually from the anti-scatter grid, for example. And then here is, example of a filter, and this is a really suboptimal filter. So we're going to go back about 20 slides or something. The Fourier transform of the rect function, right, is a sinc, right? And then by duality, remember, we know that the Fourier transform of the rect kx is sinc. So if I have sinc in the spatial domain, right, in x, in my frequency domain, I have basically a rectangle function. So this is a trivial filter. This says, if I can't sample these frequencies out here, I should just get rid of them, right? And to get rid of them, you would convolve your image by this thing, right? Which is the Fourier transform of this thing, right? So this, if I convolve my image by this blob that runs through the picture, it's going to take out those high frequencies. Okay, where are we at? 11:47. Oh, that's good. So we're making up time because we'd fallen behind a little bit. And so now I think we're going to move on to CT. And any questions about that stuff thus far? No? Let me get here. Do I have? No, let's go back here. I think that's okay. All right, we're going to look at some CT, which is good because the projects are coming up, and we'll talk about that for a minute at the end. So Princeton Links chapter 5 and 6 goes over CT, but also the book that I recommended, Bushberg. If you buy a secondhand one online, chapter 10 is very good. But there are a myriad of books on CT that you can find the one that you really like if you want. So here's the imaging device. We've looked at it before. There's about a 50 centimeter diameter volume in there that will cast an X-ray shadow on the detector. There's a highly controllable table that is accurate to within, say, 1/4 millimeter or so. And so you can move that table back and forth to position somebody inside your beam. And this guy is getting ECG leads placed on his chest because they're going to trigger the acquisition to his heart. Okay, so they'll take some ECG, a continuous ECG, and then at a certain point in the ECG, they'll take a picture. And so it's at the right phase of the heart cycle. It's also good in many cases just to have an ECG on a patient, because then you can tell how nervous they are, for one thing, right? So sometimes you get people and you just roll them in the scanner and you watch their heart rate go up, and it can get a little crazy. And so then the tech can calm them down, go in, hold their hand, stuff like that, just calm them back down. And so it's good to have physiological monitoring when you're scanning. This thing is, instead of having a person with a big, syringe push contrast into the patient, this is a robotic version of that. And you just fill it with contrast and it pushes it at a very precise rate. So it'll put, say, 5 cc's per second of contrast through a catheter. And this is local ECG measurements here. So this basically is what brain looks like when you inject contrast into it. If you can see beyond this, the hardest thing in CT in the early days was seeing through this bone, right? So that you could see soft tissue contrast, because the X-rays were absorbed so highly by the bone, it caused great edge effects. But then if you inject a contrast agent, you can get these ridiculously high resolution pictures of angiograms of people's heads. And so if somebody's having, transient ischemic attacks or something like that, and you're trying to find a source for that, then you get these beautiful pictures of their brain. You can very quickly get a large field of view of vascular and soft tissues. So this exam, they have a very fast rotating gantry, high helical pitch, it's called, where the patient just zooms through in about a second, and you get all of these data. In modern CT scanners, they are compensating now for high X-ray attenuators like hip implants, cardiac pacemakers, things like that absorb X-rays very highly. And so they cast a really hard shadow. And so if you just do standard reconstruction, you can see that there's this huge artifact from missing signal between the two hips. This person has 2 artificial hips, right? But when you take into account that those hips are there and you do some smart analysis, you can get rid of that artifact, or at least reduce it a lot. You can measure cardiac function and size and location or the state of vessels very quickly with this technique. And you can orient, you now have a full 3D image, and so you can orient it in any subsequent orientation just by putting it into something like this, which is Osiris, which you can cut different planes, or look at it in 3D. We saw one of these, and this is just a phenomenal, coronary angiogram taken in 150 milliseconds in a patient, right? And so, I did MR for, I don't know, 30 years or something, 25 years, and we never saw anything like that, right? In 150 milliseconds, you don't get much signal in MR, but in CT, 150 milliseconds, you get a lot of signal, and you can make these fantastically high resolution pictures really quickly. So I think it's a very sort of applicable imaging modality for all of cardiac. The only problem right now is it's too inexpensive, which sounds strange, right? But it is actually too inexpensive, in that if you run a cardiology clinic and you do these studies, you can only bill a certain amount of money. And so the tests that are competitors with this right now, you can bill 4 times that. They're not as good, but you can bill 4 times that. And so it's really hard to get people in practice to replace a machine that makes them 1/4 the money, right? So that's American healthcare. In Europe, like in Britain, because all imaging is a cost item, it's not a revenue item. There, if you go into the hospital and you have chest pain, the first thing they do is a CT. just like, let's see what's going on. Boom, because they can most efficiently get you into the right pathway after that, you know, for the lowest cost. So this is CT of these coronary vessels. So if there is an abnormality in one of these vessels, it shows up pretty easily. CT of a beating heart. So what you're seeing here is really the contrast agent that's in the chambers of the heart. And then you take a sequence of these images that take 150 milliseconds, and then you play that sequence of images back as a movie, right? So that's like 7 frames per second or something like that. And it looks like this. So you get this ridiculous functional information. Like that's the left atrial appendage contracting up there. Don't see that anymore. Here's the left atrium. You know, you can see the left atrial walls contracting, etc. So the first generation CT scanners, going back about 30 minutes, you had a X-ray source and a single detector. And this was Hounsfield in his lab. This is how he did it. He would just like raster a source past the sample and have a single detector. In fact, he didn't do it with X-rays. He didn't do it with an X-ray tube. He did it with something that was radioactive with a small pinhole. So he just had, you know, basically gamma rays, high energy X-rays coming out, and he rastered that across instead of actually producing it with a X-ray bulb. So then you rotate and you raster at a different angle. And that produces a lot of, so this is a mock-up of what Hounsfield did in his lab at EMI back in the 70s, right? He had this detector here and a source here. And instead of changing the angle, this was on a rotating table, and he just clicked the angle and then scanned again, and then clicked the angle and scanned again, right? So this thing, instead of rotating all this gizmo, he rotated the sample around, right, to get all of the projections through the sample. You could do that with people, right? You could like put them on a stand and rotate them and image them with a chest X-ray machine, right? And you could make a CT that way, but they'd probably move around a little bit. They'd get dizzy. They wouldn't like it. And nowadays they rotate very fast. And so they sped it up by putting a few more detectors over here, did the same kind of thing. And then they sped it up a lot by having a fan beam and then a lot of detectors down here. And it's been 1,000 detectors down there for a long time, right? It was sort of sufficient resolution. And then along comes multi-slice, where you say, okay, I've got this detector array. What if I stacked detector arrays one on top of the other, right? Can I go faster? And yes, you can go faster. So if I put 4 detector arrays stacked one on top of the other, I can go 4 times as fast to scan the whole body, right? And so nowadays, a modern detector, as you've seen those examples, you've got about 1,000 elements this way and upwards of 256 this way. So it's like having 256 of those original fan beam scanners stacked on top of each other, right? So that's why you get an image of the heart in 150 milliseconds, because the whole heart projects onto this detector, right? So you can see the entire heart, and then when you rotate around, you get all the data you need. Siemens did an interesting thing, and they built a scanner that has 2 X-ray tubes and 2 detectors, and they're pretty well 90 degrees apart. So essentially, you're getting a much higher angle view simultaneously, and so you're scanning twice as fast in that case. And so that they went down that direction, as opposed to making their detector in Z very large. They kept their detector in Z at about 8 centimeters or something, maybe 6, but they put 2 of them in there, and they spun it really fast, and then they would zip the patient through fast, right, to get Z information. And the way you zip the patient through is, while this thing is rotating, you use that really highly accurate table just to push the patient through at a certain speed, and you get a a set of spirals projections, right? It's like a helical pattern of projections through the patient. And if I have a helix and I have one point at the apex here, then it goes around and I have my next point here, right? I can interpolate between those 2 points to get anything in the middle. So that's what they do. So if they need a whole set of points in a plane that falls between those two, I'm going to use the interpolated value of those 2 points, right? To get a full volume of data. Works really well. That works really well, that helical scanning, unless you're imaging something such as a heart when it's arrhythmic. So if you need to make an image of an object, but that object is continuously changing, right, from beat to beat. So if one heartbeat doesn't equal the next, it looks different as you go down through these helical spirals, and it causes artifacts. Another way of doing it is just to step the patient through. And this is done when you have a wide detector and you want to do the whole body. Sometimes you push, say, 16 centimeters, take a picture, go another 16 centimeters, take the next picture, go another 16, take the next picture, as opposed to doing a continuous helical acquisition. This is the scanner we have here over in the Jacobs Hospital. You know, from a really nice GE marketing video. They're really great at making marketing videos. These companies go all out, man. And they're really terrific. So here's the detector down here, X-ray tube up here. This is a massive power supply to create the voltage across the anode cathode in the X-ray tube. This power supply is a really special one. It can flip between 2 voltages in sort of the kilohertz range. So it'll do 80 kV across the tube and then flip to 140 kV and then flip back to 80 kV and 140. And so the image you get is interdigitated energies, right? And so it's kind of like simultaneously dual energy imaging. So you take up all of your 80 kV data, make a picture, take all your 140 kV, take a picture. And it's basically taken at the same time. So they went deep into that engineering territory to make an amplifier that could do that, right? To produce enough X-rays. This is what it looked like with the skins off when they were installing it here. And here when you download the PDF of these slides, you can take a look at some of these movies online where engineers have taken the covers off the scanner and then turned it on and just to watch it spin really fast. It's somewhat entertaining. That's a more accurate depiction of the Siemens model. One of the detectors is slightly smaller than the other, but the 2 tubes are identical. And here it is rotating that movie. So that's how fast the patient goes through it. Okay. So they zip it up, and this is in real time. And then if you don't have enough X-ray power, you can slow the thing down such that you get enough X-rays per unit time to make the picture. But when it's really gunning, they can go that fast, right? And so I've been in this scanner going that fast, and it's pretty interesting actually. So the usage of CT, I mean, it's omni usage in medicine worldwide. These data are pretty old. These end in 2008, and this is probably Medicare usage. Yeah, you get accurate data from Medicare on usage. Getting accurate data for any type of American healthcare delivery is exceedingly hard. Kaiser might have some, you know, with a sizable set, but it's not like Denmark, right? Or Scotland. Like every single person is on the same database, right, in those countries. And so they're generating these massive databases of healthcare records, which are giving them a huge leap in AI, right? Because they actually can put all this stuff together. Whereas in the States, it's all just like separate, and you can't even get it inside your own institution. Some departments say, oh no, that's special data. We can't share any of that data because it could be valuable. so it's very difficult here. But Medicare and the VA has a lot of data, but try and get it. So helical CT happened here. So this was all before helical CT. And the one thing about helical CT, which is the magic, was you could read out signals and power everything on the detector through brushes. And there's like copper ribbons on the outside of the gantry, and then you had conducting brushes. So all the signal went across that. So now you can just rotate it in one direction continuously. Before that, they were all ribbon cables, as you have seen, and you plug it into the thing and then you run the ribbon cable. So you can't rotate that continuously, right? That winds up, and so you have to wind it 360 and wind it back, and then wind it 360 and then wind it back. And so that took forever, right? Helical CT, and Siemens was the basically proponent of this. They came up with these gantry detector things. So at that point, the use of CT started going way up because the pictures just got really good, and it was a lot cheaper, a lot faster. And then multi-slice with helical. So now this was when we had one detector row. And then here in 97 or something, we said, oh, let's do 4 detectors, 8 detectors, 16 detectors, 32 detectors, up all the way. And, you know, now if you are in a car wreck or you fall off a ladder or anything and you show up in the ER, definitely you're going to get a CT, right? Just take a look, right? See what's going on. It's cheap, easy, fast, you know. So, but it's used a lot. And you don't need to know this table. This is all the generations of people like to teach that. Anyway, I don't know why. So I would watch this video because it's one of these high-end marketing videos to show how their detector works. It's really cool. This is the anti-scatter grid. This is my handheld video at the plant where I took my phone and I just passed it along over top of the thing, and you can see how things come and go. So they're all on a base here. That's what's down. But then when you look up, you can see it'll disappear at a certain angle. Interesting thing is it comes back and then it disappears again, right? It's like, what the heck? What good is that? But that's because this is light, right? And light is like bouncing, so you get multiple images. But the X-rays would just like disappear, right? Okay, now where are you at here? Right, 07. So we got 13 minutes. Okay, good. So the fundamentals of how CT imaging works and what signals we're going to take in order to take a really good picture, we'll describe in the next few slides. And so here's a point source of X-rays, ideally. Here's our detector. And here's the patient casting a shadow on the detector, okay? If I look along one line here, and I know what that line is because I know where my detector rotation angle is, and I know where I am on the detector element. So here, I know I'm looking straight through the patient along this line. And I know that I'm not seeing many X-rays. Right, so most of the X-rays have been absorbed along this line. The reason is there's the patient's sternum here, which is a big bone right in your chest. There's the aorta, which might have some contrast in it, and then there's the spine, and the spine will absorb a ton of X-rays, right? And so it casts a very deep shadow, right? We don't see many X-rays there. However, along this line, along here, and I just plot what I see in this detector element right here. And because where the gantry is, I know where the gantry is, and I know where my detector is, I know the line through the patient, or at least I know the line through the imaging volume. I know it's this line along here, and it's mostly air because the lungs are principally air. There's some muscle up here, muscle back here, maybe a rib. And so I get quite a few X-rays. Out here, this very edge of the detection thing is essentially how many photons were released from my X-ray tube, because they haven't hit anything other than air. And air has negligible attenuation, right? So if I have a clear shot through air, then I see a lot of X-rays are counted in my detector, okay? So there's my shadow, right? And it's at this angle. Now I click the gantry along in a controlled fashion, and I measure a new shadow at a different angle. And still in all, I know exactly which detector I'm measuring. I know what angle the gantry is, so I can draw this pathway back through the imaging volume. So I know that the sum of attenuations through that pathway produces an X-ray measurement of this amplitude, right? And so this, shadow just changes dynamically as I rotate my gantry around. I just keep the X-rays on, right? Keep them on the whole time, and then I'll just sample out what the signal is every, I'll do it maybe 8,000 times for a 360-degree rotation. Right? Here's a benchtop system. This is a really upgraded version of what Hounsfield made. This is an X-ray tube that is probably from a mammogram system. So this is small. And then all of this gizmo is research by this person. This is a friend of mine at Hopkins. These aperture things that he changes in order to filter the image before it gets to the detector, or filter the X-rays before it gets to the object. And then here's the object. And then this is just a detector panel you can just buy off the shelf for any old X-ray system, right? So you lock that in, put it all on an optical table, and then to do CT, you have this controller where you just rotate the object. So it's that same way that Hounsfield did it. This is it's a really cool way to do experiments. It's not that expensive to set up, and most X-ray labs have something like this set up in them. Speed gains. This basically the number of samples per time that are obtained by a CT system has gone up with Moore's law, almost precisely. This plot was made by Norbert Pelk, who's at GE, and it's essentially, raw data points per second for CT just goes up as Moore's law. So that gets you from here, where you had a 80 by 80 image every 20 minutes, to here, where we have a 320 by 512 by 512 image. It's a lot of voxels, right? I say it's every 150 milliseconds, but because you only need half the projections to make the picture. In order to image that fast, the engineering that had to go into making really bright X-ray sources was part of the package, right? So GE, Siemens, Philips all had teams working on making X-ray sources that were bright enough such that in 150 milliseconds, you could get enough X-rays out of that thing to make a picture, right? And so it just got bigger and bigger and bigger in terms of the X-ray dynamics. And here we'll recall from lecture about X-ray physics that the source, right, has some kind of spectrum, right? So there's this is the density of X-rays as a function of energy, right? And this helps create a specific look of images from a different manufacturer. They'll change this spectrum with filtering and stuff like that, make it harder, make it softer. And you can see the difference in different manufacturers, say between a Canon scanner and a Siemens scanner. So just to review, if I have a substance, let's say this is muscle, right? And I have X-rays going in, and they pass through some distance of the material, and I count how many come out, there's always going to be less, right? I can't generate more X-rays, right, by shining X-ray light into an object, right? Probably in some physics labs in the world, you can do that, but for this experiment, we don't do that. We just see how many get absorbed. And this is the fundamental relationship as we learned in physics, right? We have an intensity it gets attenuated by this simple factor with a linear attenuation coefficient characterizing the substance. And it's a simple mono exponential. Okay. And I think we did this already, right? We looked at this derivation. Okay. An inhomogeneous slab of material, if I put n0 number of X-rays that hit the slab, and then as I go through the slab, the linear attenuation coefficient changes as a function of position through that slab. It's not constant. It changes. Then I just have to put in that function, right, for what the linear attenuation coefficient is as a function of depth through the sample. And then just put it in the same formula, right? And that will give me my number of photons that are coming out the back, right? So this function, right, in one dimension here, this is going to be our image. It's like, what is mu as a function of position? What's the linear attenuation coefficient as a function of position in my object? That's what we're going to figure out, right? If you wanted to do this absolutely precisely correct, and there are ways of doing image reconstruction in which this is all taken into account. The problem with them is they take a long time to compute, right? But the intensity, when you look at its real mathematical description, you not only have depth dependence of mu, you have energy dependence of mu. So mu depends, is it 80 kV, is it 120 kV, et cetera. It's going to have all these different dependence. And your X-ray beam has this density of X-ray energies, right, as a function of energy. So you really should integrate over all of those energies with these weighting factors. The brightness intensity goes as the energy, so energy is in there as well. And the mu should participate in that integration over the energy, right? And so that becomes a more complex inversion to figure out what mu is. And you then are going to get a mu at different energies as well, right? You're not just going to get a one value of mu for your image. I think we'll stop there. We'll start with this mathematical description of what projections are, et cetera, next time. Dr. Liu and I will talk today briefly about timing of the project, but we're going to put up a document that gives like relevant dates and things like that as to when we need to know what project you're going to do and when we need to get teams together. It looks like we're going to have teams of 3 people in order to have half the people present, half the people do videos. And then for MRI, the people who did videos for CT will present, and the other half will do videos. Okay. And that's the plan. It looks like when I counted the people, it looked like there were 81 people or something in the class. So I think it'll work out with 3 per team. Okay.